Hi, Assalamualaikum and good morning. Today we are going to continue with second law of thermodynamics part 2. Alright, previously we learned that from a second law of thermodynamics, which is from Kelvin Planck's statement, they state that there are no heat engine that can have an efficiency of 100%. Right, then we might wondering, so if not 100%, what is the highest efficiency that a heat engine can possibly have? Right, before we can answer this question, we need to define an idealized process first, which is called a reversible process. So what is a reversible process? Okay, a reversible process is defined as a process that can be reversed without leaving any trace on the surrounding, where both system and the surroundings are returned to their initial state at the end of the reverse process. Example of a reversible process are frictionless pendulum or a quasi-equilibrium expansion and compression of a gas in figure 6.29. Right. Meanwhile, a process that is not reversible is called irreversible process. Now, can you think of any example of irreversible process? So as you can see here, a simple irreversible process can be seen on a cup of hot coffee. Okay, once the hot coffee cools, it cannot heat up by retrieving back the heat it initially lost to the surrounding. Okay, a reversible process, okay, this process actually did not exist in nature. They are just an idealization of actual process. A reversible process can be viewed as a theoretical limits for the irreversible process. Okay, we may never be able to have a reversible process, but can certainly approach it. Okay, the more close we approximate a reversible process, the more work delivered by a work-producing device such as turbine, or less work required by a work-consuming device such as compressor and pump. Okay, now factors that cause a process to be irreversible are called irreversibilities, which include the following: friction, unrestrained expansion, and so on. Alright, the presence of these factors cause a process to be irreversible. Okay, for example, consider a piston cylinder here, right? Where this is your system, gas is your system, and outside the system is your surrounding. And consider this as state 1, right? Okay, now when the piston move downward, okay, when the piston move downward, a friction force develop at the interface. There is a friction force here at the interface between the piston and the wall face, right? Okay, then therefore additional work is needed to overcome this force. Okay, then this work will eventually converted to heat and transferred to the surrounding. Okay, so we know that this is your state 2, where you have a compression process here. This is state 2. Okay, we know that we can return back the system to the original state, which is state 1, by expanding the gas, right? But then how about this Q? Right. Okay, now we have this we're going to have this expansion process in order for a system to restore back to the original state, which is state 1. So this is your expansion gas, right? Okay, now when the process is reversed, that is the piston is moving upward, okay, the interface does not cool, and the heat release does not converted back to work. Okay, instead the interface the interface here will heat up again due to the frictional force over here that is against the motion of your piston, right? Okay, since only the system are restored back to its original state, but not the surrounding, because Q here is not converted back to work. Therefore, the process is irreversible. Okay, another example of irreversible process is fast compression and expansion, as well as unrestrained expansion. Another example of irreversibility is heat transfer through a finite temperature difference, as you can see in figure 6.33a. Okay, we know that heat is transferred from the warmer room air to the cold soda. So initially you have a cold soda with temperature of 5 degrees C. Okay, if you put in a room air, or if you left in a warm room, eventually this soda will absorb the heat from the room, which will increase the temperature from 5 to 20 degrees C. Right, now, can this process be reversed? The only way this process can be reversed and the soda restored to its original temperature is to provide refrigeration, which requires some work input. So let's draw the process first. Initially, you have cold soda, state 1, with temperature of 5 degrees C. And then what happened in state 2? Alright, in state 2, heat is absorbed from the room air, and the temperature of the soda increased from 5 to 20 degrees C. Now, can we reverse this process so that we can get back the original temperature of soda, which is 5 degrees C? We know that we can do this by provide a refrigeration where we put the soda in the refrigerator. So this is the refrigerator, but you need to supply some amount of work to the refrigerator. So eventually the temperature of soda will drop to 5 degrees C. Okay, so you can see that soda the temperature of soda can be restored, meaning that system can be restored to its original state. But how about the surrounding? We know that reversible process can be occurred if there is no change in the system and the surrounding, right? Alright, if we recall the refrigeration cycle that we have learned earlier, so you have a refrigeration cycle which require input, and you need to absorb some amount of energy from the low temperature source, which is the refrigerated space, which is where your soda is in. So this is where your soda is in, right? And then this refrigeration system must sink some amount of heat QH to the surrounding. But in this case is your room lah, or your room. Right. And then we know that what is QH? QH is equal to QL plus W in. Okay, you know that you requires this amount of heat. For example, this value 5 joule to increase the temperature from 5 to 20, and then uh, you also need to release the same amount of this heat, 5 uh, 5 joule, in order to reduce the temperature from 20 to 5 degrees C. This is where your heat from the refrigerated space is absorbed by the refrigeration cycle here. So this is 5J. So you know that your QL is 5J, for example. And the heat released to the surrounding is equal to QL plus W in, which means that you have additional amount of energy with the same magnitude with the work supplied to the refrigerator, meaning that the surrounding did not restore to its original state, because originally you have a surrounding lost this amount of heat, but then gain 5 joule with the additional energy equivalent to the work supplied to the refrigerator. So surrounding did not restore to original state. So we can conclude that this process is irreversible because only the system can be restored back to its original state. Alright, now if you look at the second figure, 6.33b, right? You have a soda, 5 degrees C. Now, can you reduce the temperature here from 5 to 2 degrees C by releasing heat to the environment? Obviously no, right? Because you need to put this soda in a refrigeration, or in a refrigerator that requires some work input in order to reduce the temperature. You cannot release it naturally. Okay. A cyclic process that is reversible can be modeled as Carnot cycle, which serves as a perfect cycle or ideal cycle, and consists of 4 reversible processes. Okay, the first process from state 1 to state 2 involve reversible isothermal expansion, where what happened here, the gas is allowed to expand slowly, doing work on the surrounding. Now, as the gas expands, the temperature of the gas tend to slightly decrease, but as soon as the temperature drops by a very small amount dt, right, some of the heat here from the energy source is transferred into the gas, now keeping the gas temperature constant along the process, right? And then the second process from state 2 to state 3 is called reversible adiabatic expansion. Alright, now at state 2, the heat source is removed and replaced by insulation so that the system becomes adiabatic. Alright, now the gas continue to expand very slowly, doing work on the surrounding until its temperature drops from TH to TL. Okay, now at state 3, the insulation is removed, but it is brought into contact with a sink at temperature equal to TL. Now the piston is pushed inward by an external force doing work on the gas. So as the gas is compressed, the temperature tend to rise. The temperature tend to rise by a very small amount because the process is very slow. So the temperature tend to increase in infinitesimal amount of T dt, right? But now this thing here helps to keep the gas temperature become constant by absorbing heat from the gas. So gas is absorbed from the heat is absorbed from the gas when the temperature start to rise by a very small amount. Okay, this process which is called as reversible isothermal compression. So this process continue until the piston reach state 4. Okay, last but not least, in state 4, heat sink. This heat sink is replaced with insulation so that the process became adiabatic, and now the gas is further compressed very slowly and returns to its initial state, which is state 1. The temperature rise from TL to TH during this reversible adiabatic compression process and complete the cycle. Okay, as you can see from the slide, okay, the first figure shows or illustrates the PV diagram of the Carnot cycle. So the first process from state 1 to state 2 is what? Is the isothermal expansion, because you have an increase in volume here, and then because it is isothermal, so T is constant. And then the second process from state 2 to state 3, still the expansion, but this time it is an adiabatic expansion. And then from state 3 to state 4 is what is the isothermal compression, so T is constant, and then you have a decrease in volume because it is compression process. And then from state 4 to state 1 is what is the adiabatic compression. And then the second figure here just show the reverse Carnot cycle, which illustrates the cycle in a reverse direction, right? Okay, so now if you see this, a Carnot heat engine, what is that? Carnot heat engine is the heat engine that is totally reversible, right? And then what does it mean by Carnot? What does it mean by reverse Carnot cycle or the reverse Carnot heat engine? Okay, so the reverse of a Carnot heat engine is what is a Carnot refrigeration cycle, right? Okay, according to Carnot principle, the efficiency of an irreversible heat engine is always less than the efficiency of a reversible one. So we can write this: the efficiency of irreversible heat engine is always less than the efficiency of reversible heat engine. Okay, and then the second principle states that the efficiency of all reversible heat engine operating between the same two reservoirs are the same. So this principle can be indicated in the first figure. As you can see here in the first figure, you have three heat engines, right? The first heat engine is an irreversible heat engine, and then the second and third heat engine are reversible. So according to the first principle, okay, the efficiency of irreversible heat engine, which is heat engine 1, is always less than the efficiency of heat engine 2 and 3 because they are reversible. And then for reversible heat engine 2 and 3, the efficiency of both heat engine are similar, are the same. Okay, now what is the second figure tells us about? Okay, this figure proves that the violation of first Carnot principle will violate the second law of thermodynamics. Okay, what is the first Carnot principle? So according to the first Carnot principle, the efficiency of irreversible must be less than efficiency of reversible. So if we violate this principle, meaning that the efficiency of reversible heat engine is less than the efficiency of irreversible heat engine. So in this figure, you have one irreversible heat engine and then you have another reversible heat engine. So the efficiency is the efficiency of heat engine is equivalent to what? W work net out over QH, right? This is from the previous previous week. This is in the earlier chapter. We know that the efficiency of heat engine equal to the ratio of W net out over over QH, right? Meaning that if you have greater efficiency, you will deliver a greater amount of work, right? So if the efficiency of irreversible heat engine is greater, meaning that you will have greater W here compared to W reversible. And then you will have a slightly low value of QL for irreversible compared to reversible. Why? Because what? Because you know that QH equal to W plus QL. So if for irreversible, you have more W, mean that your okay. If you have the let's just give a number for QH here. So for example, QH is 100 kilojoule, right? If the first heat engine have a greater efficiency, for example, it will deliver about 80 kilojoule, and then the second reversible heat engine will deliver only about maybe 60 kilojoule, and then the rest is what is your QL. So 100 minus 80 is 20, and then 100 minus 60 equal to 40. So your QL here for irreversible is lower than QL for reversible heat engine, right? And then if okay, for a reversible heat engine, you know that reverse heat engine is actually a refrigerator, right? Okay, if we combine these two, if we combine the irreversible heat engine and the refrigerator, the reversible heat engine, now you calculate what is QH net here. QH net is equal to QH minus this QH that going out, QH, and then what is W net out? So you have W net out here is greater than reversible, so W net out W irreversible minus W reversible, because for heat engine here you have W out, and then refrigerator you have W in. So that's why W irreversible minus W reversible. And then What is QL net? QL net is what? Q that goes to the TL, to the low temperature reservoir, minus the, sorry, what is the QL net here? QL net is the Q in that goes to the refrigerator or reversible heat engine minus QL that goes out from the heat engine. That because because the direction is reverse for a heat engine compared to the refrigerator. That's why you have QL net equal to QL minus QL reversible minus QL irreversible. Okay. So for QH, you will have no QH because QH minus QH is equal to 0. So what does this figure tells us about? So this figure violates the second law of thermodynamics because there is no sink of heat, because according to second law of thermodynamics, okay, you must have a heat transfer between two reservoirs, right? So that is what it means by the second figure. Okay, now moving on to the thermodynamic temperature scale. It is a temperature scale that does not depend on the property of a substance, which is applied to a reversible heat engine or a perfect heat engine. So because we know that a reversible heat engine is a perfect or ideal heat engine, which is not exist in a real life. Okay. Okay, according to the thermodynamic temperature scale, the temperature ratios depend on the heat transfer ratio between a reversible heat engine and the reservoir. So we can express the ratio of QH over QL equivalent to the TH over TL. Okay, this temperature scale is called Kelvin scale, and the temperature on the scale are called the absolute temperature. Alright, and then give this figure 6.43 just to show that for a reversible cycle or for a perfect cycle, the heat transfer ratio QH over QL can be replaced by the absolute temperature ratio of TH over TL, which satisfies this equation. Now, based on the thermodynamic temperature scale just now, we can have another expression of Carnot heat engine by substituting the ratio of heat transfer with the ratio of temperature. Okay, previously you learned that the efficiency of heat engine is equal to W net out over QH, and we know that QH can be expressed as QL plus W net out. So we know that W net out is equal to QH minus QL. So substitute this equation into here, we get efficiency equal to QH minus QL over QH, or also can be written as QH over QH is 1 minus QL over QH. This is for any heat engine, but for a reversible heat engine or a perfect heat engine, we can substitute this ratio with the ratio of temperature. So we have a new expression for Carnot heat engine. And this figure just to indicate that no heat engine can have a higher efficiency than a reversible heat engine. Okay, no heat engine can have a higher efficiency than a perfect heat engine. We consider reversible heat engine as our ideal heat engine or perfect heat engine. So efficiency is lower for irreversible heat engine and equal to this reversible heat engine, and then efficiency greater than reversible is a impossible heat engine. Right now, let us examine how the thermal efficiency varies with the source temperature, source temperature when the sink temperature is held constant. So TL is held constant at 303K. Now we're going to varying the pH value and see how the thermal efficiency value is. Okay. All right. Now the thermal efficiency decrease as the source temperature is lowered. For example, when the heat is supplied to the heat engine at 500 Kelvin instead of 925 Kelvin, the thermal efficiency drops from 67.2 to 39.4%. So this is a fraction of heat that can be converted to work, which dropped to 39.4% when the temperature of source drops from 925 to 500, right? And then as you can see here, when the source temperature TH is dropped, is reduced to 350 Kelvin, the thermal efficiency become just 13.4%. So this efficiency values here shows that energy has a quality as well as a quantity. It is clear that the thermal energy values here, okay, more of the heat temperature thermal energy can be converted to work, meaning that at high temperature we can convert more thermal energy to work. So therefore, the higher the temperature, the higher the quality of energy. Similar to heat engine, we can also use the relation from a thermodynamic temperature scale to have a new expression for an ideal refrigerator and ideal heat pump, or reversible or Carnot refrigerator and heat pump. So we learned that for any refrigerator or heat pump, previously we learned that the coefficient of performance can be calculated using this formula, right? And based on the thermodynamic temperature scale, we can replace the ratio of heat with the ratio of temperature. So we just replace it here and we have a new expression for Carnot refrigerator and Carnot heat pump, or perfect heat pump and perfect refrigerator. And given here that no refrigerator can have a higher COP than a reversible, because this is according to the first principle of Carnot, right? Because the reversible refrigerator is our perfect refrigerator. So no refrigerator will have a higher COP than our perfect refrigerator, our reversible or our Carnot refrigerator that operate between the same temperature limit. So as you can see here, you have three refrigerator operating at same reservoir. Okay, so the first refrigerator is the reversible, and then the second is the irreversible, and then the third one is the impossible refrigerator. So now looking at the value of COP value, so it is proof that the reversible refrigerator will have a COP higher than irreversible refrigerator. But for impossible refrigerator, it is impossible to have a refrigerator having the COP value higher than our perfect refrigerator. So if you have a COP higher than COP reversible or ideal or perfect COP for refrigerator, that refrigerator is impossible. So to summarize, the coefficient of performance for refrigerator, if it is less than the coefficient of performance for reversible refrigerator, it is a irreversible refrigerator. And if the COP of refrigerator is equal to the COP reversible, it is a reversible refrigerator. And if the COP or coefficient of performance for refrigerator is greater than coefficient of performance for reversible refrigerator, it is an impossible refrigerator. So the COP, coefficient of performance of a reversible refrigerator or heat pump, is the maximum theoretical value. So if you are asked to calculate the maximum COP, okay, you can calculate it from the COP reversible. Right, and then actual refrigerator or heat pump may approach this value as the design are improved. So if for an actual or real refrigerator, the value of the COP can be improved if they improve the design, but they can never reach the COP value of your reversible refrigerator or heat pump. The COPs of both the refrigerator and heat pump decrease as PL decreases. That is, it requires more work to absorb heat from lower temperature media.